So here's a quick summary, because the panopto didn't work, and I think this is an important topic. So when considering changes of variables, the idea is that we consider first the UV plane, and we move to the xy plane. Via a function, x is equal to x of uv, and y is equal to y of uv. Now if we zoom near a point, and we look at how to approximate this change, if we take the linear approximation of this change of variable, what do we get? If we pick a point uv, and look what happens when we move a little bit away from the point. So here we're going to have u plus du. Over here we're going to have u comma v plus dv. This is very similar to what we did in linear algebra, in the algebra section. So the image of the point uv lands at xy. We can look where the images of the displacements land up. And so this point over here will turn out to be x plus xu du, comma y plus yu du. So let's explain why that is. Over here, what we have is that we want to look at the image under x of the point u plus du v. So we look at the image of that point. And this is approximately by lecture 11 is equal to x of uv, the starting point, but we're going to move it a little bit. And how much do we move? We move by dx by du to du. Similarly, y of u plus du, so the y coordinate of this point here is approximately y of uv plus dy by du. Again, this is at uv times dv. And similarly, for this point up here, we get x plus xv dv, y plus yv dv. So because this is a linear transformation, we can give the matrix form. And we just need to write down the vectors, the red vector and the blue vector, because that's the image of du and dv, appropriately scaled. So the red vector would give me xu, yu, and the blue vector would be xv, yv. This is also known as the Jacobian of the transformation from xy to uv. Now the area change, the absolute area change, is the absolute value of the determinant of this Jacobian. And this leads us to the theorem that if I have a change of variables, the double integral over the domain of a function of x and y is equal to, when you integrate over a different domain in the uv plane, of f of x of uv, y of uv, and we need to throw in this factor, this area change factor times du dv. The idea is the area here and the area here are different, and the scaling factor is exactly the determinant of the Jacobian when you take the absolute value. So I managed to get through a couple of examples in class. So the first example being polar coordinates, where x is equal to r cos theta, y is equal to r sine theta. And so we have that the Jacobian in this case is equal to cos theta sine theta minus r sine theta, r cos theta, and the determinant of this, and the size of the determinant of this Jacobian is just r. It's r cos squared theta minus because of plus r sine squared theta, and that's just r. Thus, the double integral over a domain of the Cartesian coordinates dx dy is equal to the double integral of the same function in terms of r and theta times r dr d theta. And don't forget this factor of r. So in this example, what we have here is the volume of a solid above the xy plane, and beneath the paraboloid z is equal to 1 minus x squared minus y squared, which is the same thing as 1 minus r squared, over the domain between 0 and 1 for the radius, disk of radius 1. So here the angle theta runs between 0 all the way to 2 pi, and the radius runs between radius 0 all the way out to radius 1. And here's that important factor we don't want to forget, r dr d theta. Sorry, I've already written the drs. There we go. And so this is equal to pi by 2 once you integrate this. So for example 1b, annulus. This is as far as we got in lectures. We're going to integrate on the annulus between a and b. So you should note that in these cases, the change of variables don't really change the shape of the domain. We're just relabeling our coordinates. So the region will be between a squared smaller or equal to x squared plus y squared smaller than b squared. And here we want to be over the first quadrant. So just between this chunk and this chunk, and below y equals x. So this chops up and I only have this piece. what we have is that the radius lies between A and B, and the angle theta lies between 0 and pi by 4. So if I want to integrate y squared by x squared dx dy, what I get is integral between theta equals 0 and pi by 4 of the integral between r is equal to a and b of r dr of the function where y squared is r squared sine squared theta and x squared is r squared cos squared theta. And this whole thing here is r tan squared theta. And since tan squared theta is just a constant with respect to r, this whole integral becomes a product of two one-dimensional integrals, and this is just equal to as a hint, tan squared is equal to sec squared minus 1. And you can remember some of your trigonometric formulas. The integral of sec squared is tan.